last speaker for today's session, Sergey Borisenko, who is known ARPAS expert, but now he is also inventor of a new spectrometer, and actually what he will speak about, I will see. Please, Sergey.
Hello, everybody. Thank you, Alexander. It is a great pleasure always to speak to such an audience. Since it is a school, I will start with a little bit of simple introduction to angle resolved photon emission spectroscopy. And this is a very short, and I think it's very sort of very easy. And this comes from the analogy between the electrons in the solid and the fish in a, let's say, a lake. So in order to catch more fish, it would be good to know in which direction and how fast and how many fishes are swimming at a given moment. So this is kind of a fisherman's guide, would be good to know if you're going to fish to a lake. So if you have this kind of a map, if you have this kind of knowledge, it is always very nice to have. So this is actually the questions which we are trying to answer using the angle resolved photon emission spectroscopy. And in order to for fish to get out of the water, we use in this case the light, and I found the pictures which actually show that you can indeed, actually not only pictures, there are ways how to catch fish using the light. So I learned it, and it's indeed the case. So this is a kind of analogy which we are using to extract electrons from the solid. Another thing is that you can use that analogy with a fish which can escape from the water. This is our electrons, and there is, I learned to my big surprise that there is a flying fish actually. And basically, this is exactly what we are doing in terms of catching electrons, because they are flying away from the solid at a very different directions. And our task is to detect and to understand in which direction and how many and how quickly they're moving. So not all electrons have enough energy to escape, of course. They could be scattered by phonons, for instance. But those which can escape, they can also come, some of them can also come back, and only the fastest of them, they can make it, and then they finally get detected. So this is exactly the detectors which we use to detect the electrons. And there are different types of the detector. There are those which are focused on the speed, and meaning that as soon as the fish leaves the water, you can immediately detect it, and then you are very confident in which direction it left. And if you wait until it loses the speed, then you can estimate its speed, and then you can calculate its speed. So this is exactly the result of our measurements. We call it ARPAS onion. This is the fisherman's guide. I find this analogy very illustrative, because here in this case, you could see this amount of information. This is four-dimensional data set where you see if you cut the onion horizontally, you will get the distribution as a function of direction and direction. You need two variables to have it to denote the direction, to define the direction in space. And you can reserve another direction for the speed. So if you cut it vertically, you will get another way of representing the data, meaning that this would be distribution of electrons as a function of speed and direction. So in such a way, with this method, we get possibility to answer our main question: how many electrons are flying in which direction and with which speed. These are the detectors which we use, and ARPAS has been already introduced by Bernd, and our detector has been introduced. I briefly mentioned these two types. As I said, there are analyzers, they're called electron energy analyzers, which are concentrated on getting the distribution as a function of direction and speed at once. This is a unit of information. And in this case, this is the so-called hemispherical analyzer. in the unit of information at a given moment of time, meaning at your screen, you get the distribution of electrons as a function of speed and direction. And what we have done is we decided to catch our electrons earlier. In this case, electrons have to go through the lens and then they're sorted by energy by hemispherical analyzer. In our case, we do it at a very short distance, very close to the emission of the electrons. And in this case, we are concentrated on the direction. So basically, we detect our electrons very close to the sample, and this gives us the distribution as a function of direction here and here. This is technology which is now patented in Germany, USA, Japan, China, and the patent is pending in European Union. It turned out it's a very simple thing, but it turned out to be not known earlier. And for the comparison, the electrons here fly around 1 meter in order to be detected. Detectors are the same kind. This is multi-channel plate in this case and in this case. And in this case, the electron fly only 12 centimeters. So nearly an order of magnitude. The very instructive, very helpful thing to have is to have both in the chamber. And I show you what you see on the screen in the same room. You see the same ambient situation. We have once we run the hemispherical analyzer, we have a distribution on the screen, angle versus energy. And when running FESUMA, which we call FESUMA, means Fermi surface mapper, then you see the Fermi surface at once at the same laboratory, at the same chamber from the same sample, basically. So this having both allows you immediately to see, to cut the onion horizontally and vertically. These are the examples of the ARPIS onions for real materials. This is the bismuth tellurium, very famous Drosophila of ARPIS experiment. You could find a lot of data on the internet and in the literature. And this is kind of testing crystal also for us, although there is interesting physics inside. So we measured it. And here you see that you can get the horizontal cuts, then you get the momentum cuts, and then you can get the vertical cuts, which show the distribution as a function of energy and momentum. Good. So with this with these possibilities, we of course trying to address very interesting physical questions, and I switch to the main topic of my talk. This is platinum bismuth 2. It is extremely interesting material, as it happens very often nowadays. The material has been known before, and there are many different types of this material. What I will be talking about is the trigonal version of this material. This is a particular crystal structure, and interesting is that even we studied the similar material earlier, actually the same, but we didn't find everything what we found now. The band structure of platinum bismuth 2 of trigonal modification is pretty difficult. So we have 5 bands, even according to different calculations, you can get even 6 band crossing the Fermi level. So the Fermi surface at the first glance is very complicated, but if one has a closer look, then there are quasi two-dimensional objects. Maybe if one looks at that, this Fermi surface would probably could see some kind of layered structure, and this probably explains why the material is cleavable. Because in order to make ARPIS experiment, one has to cleave the crystal if one of the methods to prepare the atomically clean surface. And this is probably the explanation why it is cleavable, although it is very three-dimensional according to number of bands and the topology of the Fermi surface. In any case, this has been known earlier, and why the renewed interest is because our colleagues, Jeroen and his colleagues from the Theory Institute in IFW, after my experimental colleagues from Institute for Solid State Research saw very interesting tunneling spectra and also transport properties. So this was a joint effort of IFW researchers. And they found out in particular that this is a wild semi-metal. As you heard, most of the Dirac and wild semi-metals were known earlier, but it was the particular crossing of the bands, non-degenerate crossings of the band in a single point has not been noticed earlier. But now it is a very interesting subject to study, and it turned out this platinum bismuth 2 had 12 symmetry-related wild nodes, and they are located slightly above the Fermi level. And of course, if the wild semi-metal, if the band structure is of the type of the wild semi-metal, then one expects interesting properties also at the surface. And these are the results of my colleagues who did scanning tunneling spectroscopy. Here you see that material cleaves gives a very nice surface. This is very important also for our measurements. And what they saw is that actually there is a type A, type B surface, which is not surprising because the material is non-centrosymmetric. And the unique property of this material is that it turned out when we cleave the sample, you can always mark the particular sample surface A, and if you cleave it again and again, you will also get the surface A. This is quite a unique situation because most of the non-centrosymmetric materials, they grow with the stacking folds, and depending on where you are at the surface, one could really see one type of determination or the other type of determination. So in this case, this is a unique and then very helpful for the experiment material, because if you cleave it, if you open it in vacuum, then it will always be either one surface or the other surface. And in order, for instance, in order to study both, we cleave the crystal in air and flip another part and glue them together. So one could select which surface A or B to study. These are the calculations, and as I said, there are interesting properties expected in case of wild semi-metals. In particular, at the surface of a wild semi-metal, between the projections of the wild points I mentioned earlier, this is the place in the momentum space where the bands cross and in a single point. So when these points are projected to the surface, between them there are states which are called Fermi arcs, and these surface states are rather unique because they are non-degenerate and they are different at different surfaces. This is termination A, termination B. They connect the wild points. Apparently, they are connected like to the one side, but if you have a closer look, this arc has a complicated shape. It goes like this. And of course, the question, yes, we studied this material earlier, but how about the arcs? We want to see the arcs since they're predicted and they should be also visible in angular result for the emission spectroscopy. And we started with a brute force approach, like at the synchrotron, you go and do very many different photon energy in order to understand the three-dimensional electronic structure. And here you see the Fermi surface maps taken at very different energies, starting from 15 to 43. This gives us an idea where we are in terms of KZ. I was talking about during the simple introduction about the two dimensions of momentum, but there is a third dimension of momentum. There is another nice analogy with this, but not for today. And to make it short, there is photon energy which can probe the KZ. So we have another direction of momentum, and this direction can be probed by the photon energy. So by comparing with the calculations and having these many Fermi surface maps, we could figure out at which photon energy we cut the Fermi surface at which KZ. For instance, if you find a certain degree of similarity between the experiment and calculations, and in this particular case, you see how this triangular shape, so you have this point and you have the side, and it is flipped in this case, so you could identify approximately where you are in the KZ. I'm saying approximately because KZ resolution of ARPAS experiment is not as great as KX, KY, but in this case, one is still able to do that. So this means we have access to all three momentum components and energy. So fully four-dimensional information about the electronic structure of this material. There is a certain degrees of similarity. We found the gamma point, the A point, asymmetry point. This is how the momentum energy cut look like they are really similar. There are always some deviations from the band structure calculated, and in experiment we got used to them, but this is very helpful because we can identify these bands anyway, and we know which feature is responsible for which calculated feature. So this is experiment, this is theory, this is experiment, this is theory. I noticed earlier that the wild points are situated above the formula. And in order to solve this question, to answer this question, we went to the central laser facility where there is a unique possibility, well, not unique, but very nice possibility to do pump probe experiments with different energy, with different harmonics. I think to this extent, this is a unique possibility. And there we did the experiment with the pump probe, meaning that usually ARPAS sees only states below the Fermi level. And in this case, with the aid of additional laser, one can pump the electrons to the unoccupied states, and the electrons from these unoccupied states can be picked up, and one could have a glance into the unoccupied electronic structure. And indeed, well, not exactly, but very close to the predicted theoretical value of 45 millielectron volts, we found that these wild points is there. There are very nice also data analysis, including machine learning in these two preprints, which show also that the dynamics in these near the wild cones is pretty similar to the graphene, where the electrons cannot decay very fast when there is no phase space. So exactly in the vicinity of the wild points, this happens, and these relaxation curves are showing this. Again, in order to find out where we are, we used FESUMA there, and we saw the Fermi surface, which was on the screen. We know what the orientation of the sample, we know the geometry, and then we go with the hemispherical analyzer and do also another cut. They also have two analyzers in one chamber. Okay, so wild points are there. How about the Fermi arcs? And this is our first attempt. We used the laser in the lab. In ARPAS, one can use very different light sources. I mentioned the synchrotron with the tunable photon energy. I mentioned the central laser facility where one excites with the higher harmonics of the laser. We have also the laser in our lab, and we have a couple of them. This one is 5.9 eV laser. This is our first attempt to see the arcs in platinum bismuth 2. And this first attempt actually showed that this is the map, the portion which we studied. And the arrows show the cuts through this momentum space. At the first glance, we were happy to see the bands. They're pretty good because laser experiments are usually pretty complicated. In the case of three-dimensional material, this is the case. But the band structure was there. It was sort of similar to the predicted band structure. And this is how the typical energy distribution curve looks like. I showed you one could slice onion horizontally and vertically, but one can slice also the slices in order to get the lines, right? So this is the slice through the vertical slice of the onion, and it's called energy distribution curve. We saw the reasonably sharp peaks here at the Fermi level. But we didn't notice the arc. But then we started to investigate higher rotation angles in order to catch more electrons, not only those which were immediately seen, but also those which fly away at very different angles. And then we realized, and I show again the screenshots of just the photographs from the laboratory, because this feature which you see here energy is horizontal and direction is vertical. This is a hemispherical analyzer. This is this unit of information, vertical slice of the onion. And we saw this feature directly on the screen. First, we thought this may be an artifact, and then we had a closer look. This turned out to be exactly the feature caused by arcs. But we have never seen these kind of features in angle resolved photoemission spectra. And it turned out that nobody has seen such features, such sharp and strong features in angle resolve and in photoemission from solids, one could safely say that. So it turned out that these small portions of the map are arcs, which we first detect with that. We saw that they are very flat. They're sitting very close to the Fermi level. And again, exactly in the places where the theory predict them to be. So these are calculations along the cut, I think the vertical cut like this, and then you could see that experimentally and theoretically, they are located very close to the Fermi level. In order to give you an idea how sharp the peak is, I compare with a very decent EDC I showed you in the previous slide. That was from the bulk state, and this is the surface state which we observed. At that time, we thought that this is the record, as I said, in the record in the history of solid states, photo emission from the solid states. But I come back to this point later. So now we know that there are arcs. We know where to search them. We went again to the synchrotron and had a closer look. You need to have a very high resolution in order to record such data. That's why this time we concentrated on very low photon energies, because the lower the photon energy, the lower the kinetic energy. The lower the kinetic energy of the photoelectrons, the higher the resolution. And I think these data are taken with, I think, 12 electron volts. And here you start to see arcs, these small points, here. It was tempting to say that this is arc, but this is not. This is this feature from the calculation. So the arcs are these small points here. Difficult to resolve at the synchrotron, but nevertheless, in the vertical slice of the onion, you can clearly see these two. This is horizontal slice, and this is vertical slice. Again, as the theory predict, these features are there. So the arcs are situated at these positions, exactly where the theory predicts them. And even at higher photon energies, where the resolution is worse, one could still probably track, if you follow what I'm showing, then you could probably track still the arcs actually at all other photon energies which we see, which we studied. And this is important because when the photon energy changes, three-dimensional structure changes because we cut at a different KZ. If we study surface states, they should not depend on the photon energy. Of course, the intensity could be a function of the photon energy, but generally they are not depending on photon energy. So this was a confirmation that these are surface states. Again, we did it at different energy and with the laser compared with the theory, so there was no doubt that this is exactly the states, and they're very well separated from the bulk. So you see how sharp these features in theory, and in the bulk there are no such features. This is exactly what is seen in the experiment. Of course, having studied the superconductors during the many years, we decided to look at the temperature dependence, because such unusually sharp peaks appeared in the superconductors. And if you see here that warming up the sample from 3 kelvins to 30 kelvins, you see that this flat dispersion turned out, this flatness and this coherence got lost. So this is a very typical sign of the superconductivity. We investigated it closer and we found another typical sign of the superconductivity. This is zoomed in picture of the Fermi arc. You see the energy scale here is only 14 millielectron volts, and the cuts from the vertical slice of the onion are here. And you see the typical sign of the opening of the superconducting gap. We call it band bending. This is how it is predicted in BCS theory. Well, I'm not saying this is a BCS standard BCS gap, but there is this band bending, which is very, this is a very good signature of the opening of the superconducting gap. So we saw it at different samples, and that's why we concluded that this is actually the superconductivity. Again, our colleagues simulated the superconductivity on the arcs, considering via the Bogoliubov-Degen formalism, and they added the superconductivity in this case to the arcs. And indeed, this was a very good qualitative agreement with the experiment. Even quantitatively, one could see that the bulk remains non-superconducting and the surface is superconducting. If we, so this is the kind of smoking gun experiment, you measure at low temperatures, you measure at high temperature, and you see how the energy distribution curve shifts. This indicates strongly that there is opening of superconducting gap. And this is in the colors red, white, blue. This is a different spectrum above TC and below TC. And you clearly see that nothing happens with the bulk, but only surface feature clearly shifts and the gap opens at the surface. So we did it in this case for several samples. We tracked the position of this peak as a function of temperature, and typically this kind of drop indicates of critical temperature. So in this case, we showed the data for 4 samples, and this is the broadest transition is shown here. So this is how the superconducting gap opens. It's not big, it's a couple of millieV, but this indicates the opening of the superconducting gap. And from these plots, one could roughly estimate the critical temperature. So there were around 10 kelvins for one surface and around 7 kelvins for another surface. They turned out to be slightly different. This is the value of the superconducting gap is in a remarkable agreement with the STM data. We have this data from our colleagues. They showed that the gap is inhomogeneous on the surface, but the average is 1.5 millielectron volts. This is exactly what I just showed. And there is a typical behavior with magnetic field, unambiguously showing that we deal with a surface superconductivity. This is also confirmed by other methods. As I said, the transport properties with the with the thin films are consistent with unusual superconductivity. And data from Oksana also showed that with approximately the same value of the superconducting gap of the order of a couple of millieV, and with the value of TC, this is a pretty good agreement with our data taken from exactly the same samples. So what does it mean? Why is this cool? Why is this important? Because in order to realize the topological superconductor, one needs to have a lot of components. The main research was along the let's find either known superconductors, let's find topological properties in them, or let's make the topological material superconducting. But this is not sufficient. One has to have a particular type of superconductivity in order to be so that it's not trivial. Not trivial superconductivity means, in analogy with non-trivial insulators, one has to have additional states which are required by symmetry. So in this case, these are long-sought Majorana fermions, Majorana zero modes, which are elusive until now. The number of experiments to detect them, apparently they were there, but then they're not. So in this particular case of wild semi-metal, we have these non-degenerate arcs in 2 dimensions already for free. So we have the arcs, and then if they become superconducting, this is a very strong suggestion that this could be a topological superconductivity. But just observation of the superconductivity on the arcs was not sufficient because we were not sure whether this superconductivity is trivial or not. So then we made further steps. Again, we took samples and started to look at the arcs even with more precision. Again, we have 2 analyzers. This is with helium lamp. You have a general orientation, the Fermi surface at once. You can rotate this. These are Fermi arcs. Fermi arc is here. You can figure out at which angle you can catch them. Then you can use the laser in order to have them better resolved. This is another laser. And then if you know a lot about how to measure the Fermi arcs, you can get this kind of image. This is a very big breakthrough in comparison, even with our previous measurements. So these are very new data, and you see how nicely we can resolve the Fermi arcs. Then, as I said, at that time, we thought that was a record. So now I can tell you, this is the record. Actually, both in terms of energy distribution, the width of this peak is 1.7 millieV. This is in terms, it's not in terms of resolution, but in terms of the sharpness and strength of the peak, signal to noise ratio and its width. So this is 1.7, and also in momentum, this is 2.2 milli reciprocal angstroms. I always put 0.0 something, and our student now postdoc, she said, this is milli-reciprocal angstrom. So now one could say about a milli-reciprocal angstrom is 1,000 of a Brillouin zone. This is a very good precision. So this is how this dispersion looks like. Already this dispersion shows you that this is a very unusual feature, because usually photo emission data are pockets. If the shallow pockets, or then the dispersion goes there. And in this case, it's kind of lost from the other side. This is the signature of the Fermi arc, because arc is not complete Fermi surface, just a portion of the Fermi surface. Therefore, the underlying dispersion should cross it, and then from the other side should disappear. This is the data and the precision which is achievable. So, having this precision, of course, one asks the question, how about the superconducting gap as a function of momentum? And it turned out that the dependence is very interesting. And as we saw this, we immediately went to our theory colleagues, but the magic word node, somehow we didn't realize that we heard from a theorist that indeed. So we have the superconducting gap, which is finite at the wings of the arc, and which is 0 in this direction. It means that now we have the superconductivity, and this data just support this. So if you compare plus 90 degrees, minus degree, and 0 degree, so you can code the position on the arcs by these degrees. So you compare this point with these two, and you clearly see the effect. And then you see how the gap closes, and then you see how this is just supporting data for the paper. And this is reproducible, so you can measure the gap near the node in different samples. You can see that superconductivity is reproducible. So now we know that there is a node of the superconducting gap at the Fermi arc. And this is already a very good, this has been shown for the top surface, for the bottom surface. Now the samples are oriented, so we can measure it more easily. Nevertheless, experiments still very difficult. And there is also very interesting temperature dependence, but this may be the next study will be devoted to that. But important thing that the superconductivity has now node. So as I said, we have a very unique object. We have we have a non-degenerate spin states localized in terms of energy, in terms of momentum, actually in terms of space too. So, and this is a very unique object, and it becomes superconducting, and it has nodal points on it. So we believe, and our theory colleagues believe, that this is the all necessary requisite for having the topological superconductivity out there. So there must be somewhere the Majorana fermions, and the Majorana fermions are usually detected in a single particle spectroscopy, if it's possible, as a single peak at a zero, at a Fermi level, or as a tunneling people say, at a zero bias voltage. Maybe you heard about that. So we are hunting for peaks somewhere at a zero energy, and we, in this particular case, it is far away from the arc, but this is still pretty sharp peak. We can find them in some other places, so we hope that maybe this would be these Majorana fermions. So at this point, I would like to stop showing the data. I would like to thank all my colleagues. These are, first of all, the people from my group who did the measurements. You see that 2 persons have origin from Kyiv Academic University, crystal growers without which would be very difficult. There's CLF people, BESI people, theorists, more theorists, and our directors, Jeroen, you heard 2 talks of them. There's the Bernd is the driving force for platinum bismuth 2. He convinced me to measure it again, and so I'm very grateful to all of them. I'm grateful to you for the attention. Дякую. Україна переможе.
Thank you, Sergey, for a nice presentation. Please, if you have some questions, it's a good time to ask. Maybe while people thinking what to ask about termination. Actually, 2 different terminations. So could you see both of them on one cleave usually or not?
No, this is a point. This is an interesting thing. So you cleave it and you always see surface one. So the guys even mark the sample, like sample holders, surface A, surface B. So you can go to the synchrotron another time, another beam time, you cleave it and it's surface A.
But in principle, it's maybe it's similar to different compounds. This is some, but stairs. Usually you have stairs, right? Right. But anyway, it's only one termination. Yeah, it's interesting.
We have terraces when we cleave. Terraces is not a problem. We have the edges, and this is where we are hunting. This is where the Majorana should be running around, right? So we want to catch them there. I can show also the data where with Fisuma, you can study many points. So the guys made 400 maps and found in which position the feature is more pronounced. And we now want to understand whether it's more pronounced where there are terraces or more terraces, trying to catch this. So terraces are there, but the surface is always the same. And this is in agreement with information that you get from tunneling.
Interesting.